let's keep this tutorial kind of informal. So we just ask questions. If you have any issues, just go ahead and ask away. Okay, so I present Graphlab 2. This is I'm doing a tutorial, but this is joined with a bunch of people. Joseph Gonzalez, Pablo, Jay, other students of Carlos, who is our advisor, and then there was a postdoc on the group working with applications using large matrix factorization toolkits, which are now getting rather popular. We also have a number of other people advising on the team, and Joe had this team, David and so on. So, Graphlab has went through a few phases. Our first phase was 0.5, which is an internal release, and we do everything in C++. We really like C++, and it's all I think is insanely capitalized. And afterwards, we have Graphlab 1, which is open source. Before June 2011 was LGPL, after which we switched to Apache public license, and now nearly everything is standardized. So it's better, but code still takes an eternity to compile. And now we have Graphlab 2, which we hope to release the shared memory version somewhere around January, so in the next month or so, and we should have a distributed version by May. And now many things are standardized, not everything, so it's somewhat more usable. So the technical design goals is to improve usability, decrease compile time, which is an issue highlighted in the first code, to get as good a web performance as Graphlab 1, improve distributed scalability. So Graphlab 1 currently we do have a distributed implementation, but it's kind of tricky to use and difficult to use, and requires quite a lot of code transformations. And more importantly, we have a lot of other abstraction changes. So there's a Carlos, my advisor, is giving a talk a little later, and I should not intersect too much with the talk, or it'll make it irrelevant. So I will not go to look at all of them. So do come to the talk for all the other abstraction changes that are going on in Graphlab 2. So ever since Graphlab 1, all development is open source. Apache public license at this website, code.go.com, Graphlab API, or our webpage, graphlab.org, which I should put in there. So this is true even for current development, current experimental code, everything I'm kind of working on. If you do just add experimental, you get all the code that's still currently under flux. So we're always looking for contributors, so if you're interested, just come and join in the project. So the platforms we guarantee the target is any x86 Linux system, GCC 4.2 and above. x86 Mac system, which is 4.2 and above as well. I believe that's on LS X 10.5 onwards. We don't have explicit support for any other platforms yet, but we welcome contributors. So the outline of the talk, I will begin with Graphlab in a few slides. And how many people here know PageRank? Good, everyone knows PageRank. Yes, so the PageRank is relatively common, everyone knows, but it seems like almost everyone knows PageRank. Sorry? Okay, nearly everyone knows PageRank, but I will be giving an overview of the PageRank algorithm. And we will see how I will give a code demonstration on how we implement Graphlab and PageRank. We'll check out Graphlab 2, we'll implement PageRank in Graphlab 2. I give an overview of all the features of the Graphlab engine. If possible, if internet holds up, I'll give a brief preview of distributed Graphlab. This may not work in your checkout. And ongoing work, however much as time allows. So, here's a fair warning. This is a preview of closely intensive development. Things may or may not work for you. The interface may still change. There's still some flux going on. And if you do the process of moving from Graphlab 1 to 2, there are still a number of performance regressions we're trying to iron out. Okay? So let's begin with PageRank. So PageRank is an iterative algorithm which, given a web graph, the goal is essentially to compute this function where I have a PageRank value on each vertex. Alpha is a value between 0 and 1. Usually the well-known value for it is 0.15. And the idea is that each vertex is kind of weighted sum of the page. The PageRank of each web page is a weighted sum of the PageRank of its of pages which link into it. And then just keep repeating this, looping this until it converges to some value. So, as a quick example, if I have a little web graph over there, so the PageRank of 5 will be something like 0.15 plus 0.85 plus the PageRank of 1 scaled by 1/3 because web page 1 only has 3 output links. And the PageRank of 4 now scaled by 1 because the page 4 only has 1 output link. And it uses perform this computation, you repeat it for every vertex, and you loop until convergence. Okay. So how do you implement this in Graphlab? So what is Graphlab? So on a high level, Graphlab comprises of 4 basic components. First, we have a graph-based data representation. We have update functions, which perform computation on the graph itself. We have a scheduler, which determines the order of update functions to execute. And we have a consistency model, which determines essentially how close this computation is allowed to operate within each other. I will get more details of consistency model later. Okay, so the graph is a data graph. Is an arbitrary. It's just it's a C++ object. It's a graph with arbitrary data attached to each vertex and edge. This is again templatized, so each vertex holds its own vertex data class, each edge holds the edge data class, and you can store whatever you want. So really, the edges are directed, so you can edit edges in any directions, but for simplicity here, I'm going to draw the edges in one direction. Sorry, I draw edges undirected. So for instance here, I could have my graph as my link graph of my web page, of my web graph. On my vertices, perhaps I could store something like web page, the URL, or maybe the features of web page itself. And of course, the PageRank value. And the edge data, I could have put some kind of link weight. Maybe I have some expert information, maybe links in bigger fonts should click on more frequently, so those have higher weights. Links with the tiny fonts at the bottom of the page don't get clicked on, so those have lower weights. So I can attach a weight to each edge as well, or really any arbitrary data. So how is computation performed? Computation is performed through the use of update functions and managed through the use of scheduler. So an update function is a user-defined function which, when applied to a vertex, transforms the data in the scope of the vertex. When the scope of the vertex refers to the data on the current vertex, the data on adjacent edges, and the data on adjacent vertices. So as labeled by that shape. So for instance, how will you implement PageRank? So this is a PageRank equation as shown earlier. So we begin with a PageRank function. We take in a vertex. We take in this this is kind of functional form. We take in some kind of variable containing the scope of the current vertex. We pull out the PageRank of the current vertex and the PageRank of the adjacent vertices and the weights on the edges, and we will compute that PageRank update. And now this is a key with regards to scheduling. So what we could do, for instance, is do dynamic scheduling where if my current PageRank does not change by very much ever since the last time I run this function, then there's no reason for me to update my neighbors again. Right, so I could have something that goes like, if my page rank value changes by some greater than X, then I schedule all my neighbors to be executed, to be run with this page rank update in the future. Okay, so that connects us to the scheduler. The scheduler is some data structure, a parallel data structure with tasks, which is a task to execute, where each task is basically one of these update function executions. So we have a bunch of processors. The processor pulls out the function scheduler, executes an update. These updates could then schedule new tasks which go back into the scheduler. And this repeats until the scheduler is empty.
So if these now 2 times in there?
Very good question. I will get to it a little later. Okay, so now we shall have source code interjection 1. So let's see if I can get this to work. Okay, how do I do this? So, firstly, how do we check out Graphlab? You go to graphlab.org. It works. Download this. Interesting. Okay. We will put the link back. So code.google.com/graphlab API. You can source, and you might need a Google account, and you can check out Graphlab. We use Mercurial for development. So you can check out Graphlab by copying and pasting this and then online. So, and then after you do that, you will need to, yes, after you do that, you may need to do a HG up v2. So the current branch is still in default, which is still in version 1. You do HG up v2 to get it into our current version 2 branch. Sometime towards the end of January, we will be merging the branches. So, ./configure will create a bunch of directories. In particular, it creates 3 subdirectories: a release directory, a debug directory, and a profile directory. And after source compilation, you go to the release directory, you build there, you get everything in -03 and this. Okay, so let's see. The colors are not so great. So I don't know if you can see the colors, but we'll be working out of the release directory here, release build. So how do we code in Graphlab? So the first thing is hex include Graphlab. For convenience, I will go using NIPS Graphlab as well, and we have a bunch of macros which introduce a for each, which is kind of useful. So I'm going to implement PageRank in Graphlab. So the first thing we need to do is to define vertex and edge data. So here we define a short vertex data which contains a single double value, and this will be the page rank of the vertex. And similarly, we define a structure called edge data which has a single double weight, which will represent the weight of the edge. And we also add a couple of constructors so that they have same values when you create them. Okay. So now we first need to define what is the graph. We define the graph type with a type that we have a graph object which does a lot of things. We have some tools of partitioning. We integrated an old version of NIPS, so you could in theory use it to do some basic partitioning stuff as well. There's some graph coloring code. We have a bunch of it's a very nice little graph abstract data structure. We are making improvements. We are making alternate versions of it for low memory usage and so on. Okay. Now, let's define a few constants. So this reset probability will be the alpha in the original PageRank update. We set it to as traditionally goes 0.15. And let's define some accuracy, which is kind of a resetting criterion, which will go like 1 minus 5. Okay. Now, so how do we write the update function? So Graphlab 2, we use an update functor model. In the earlier Graphlab one, we used straight functions, and we found that to be kind of troublesome for users because we ended up introduce a lot of strange types in the system. So we use functors. So your PageRank update is implemented as a class. Let me add more. Let's see. Okay, it's implemented as a class which inherits our iUpdate functor object, which is an interface class. And what is somewhat unusual is that the iUpdate functor takes in as a template argument the class itself. So for those of you who are not familiar with this, it could be somewhat unnerving, but it's standard C++ template pattern. Okay, so let's go on. Public void operator. Okay, so we use the operator parents to define the actual contents of the update function. So, as stated earlier, in the pseudocode, you are given a vertex, you're given a scope. So now we centralize all of these into a single object called context. All the information you need about the local area of the graph, including what is the current vertex, what's the shape of your, how many edges do you have, what's your inner neighbors, outer neighbors, and so on and so forth. Okay. So now this will be the exact update function. So first we take context of vertex data, gives us the vertex data in the center of the scope. Let's take a backup of it. Let's store the old value. And now this code is exactly the sum in the PageRank equation. So we loop over all the in edges of the current vertex. We take the weight of the edge. So this for each is a macro which is extended from the blue square implementation, and all it does is that context of in edges returns really a structure of some parameters which lets you iterate over just all the images, and for each will give you one edge at a time as you go through it. Right? So you pass the edge into its const edge data, you get the information on the edge itself. So this gets me the weight on the edge, and then we multiply it by the vertex data on the source of the edge. So this is the incoming edge. We accumulate a sum, we scale it by the reset probability, which is the alpha value earlier, which is 0.15. And then now we write it back into the vertex data. We took a reference to the data on top. So this will bring to a reference to the data on top. So this write will actually transform the vertex data. And now this is what I just pasted. This is that rescheduling code array. We loop over all the out edges this time. So this is the same for each structure as well, but this time we loop over only all the out edges. We compute the residual gap, which is if I change by this much, how much will I affect my neighbor? And how much I affect my neighbor is the estimate of my change. The estimate of my change multiplied by the weight of the edge to my neighbor. And if this error is greater than some epsilon, which in this case we set that to be 1 minus 2 or so, then we issue a schedule command. We perform a schedule of the target of the outage to be executed with the page update. Okay. So that's it. This is the entirety of the PageRank update. I am probably a sequence error, so I think it's code here. Okay. So let's create a synthetic. Let's create a synthetic graph. I will define a function called create graph. It takes in the graph type as from before, and all we're going to do is add 4 vertices with initial value 1, and we'll add 4 edges in a circle with edge width 1, and now I'm going to put in the main function. Okay, so this adds edges. So we provide a series of a collection of command line parsing utilities. So for command line options, it parses command line options. I will show you what it does later on. We create a core object which kind of manages the entire Graphlab state. We set the options as part of the command line. We call create graph to instantiate the little 4 vertex cycle above. Schedule all is a convenience function which takes in a PageRank update functor as constructed above and issues and just schedules inserts in the scheduler for all the vertices in the graph. And we call start. Oops, sorry. We call start. Start tells me the runtime, and we offer the runtime. Okay. Now let's see if this thing compiles. Rule is getting long. Let's see. So we run, whoa, it's way above the screen. I can't see at the top of the screen. Okay, it's okay. You don't need to see the right. Only the left is important. So all we get is a runtime and it goes 0.0002 seconds. Okay, and we can go see the command line options by. This would be nice if I can. How do I move the window? Just close this one. So these are the default set of command line options. We can set number of CPUs, engine, which is kind of only one type. There are a few other options I'll get into a little later on. Okay. But first, one thing we should do is let's try to get the output of what we just ran. So let's go back to the source, and one thing I can do very quickly is just, since the graph is just abstract data type, I just go loop over all the vertices. For vertex ID equals to 0, the number of vertices, I just output the value of the vertex. And this after it runs. I can't do this so too frequently. We get a number, which is expected because the cycle it will just be uniform distribution. Okay. So now one thing we can do as well is we can load graph structures from files. So for instance, we can go to snap.stanford.edu. And we can download graphs from. We can download some of the graphs from the large networks here. Yeah, you can download graphs here. We have a parser for it, and it's easy to. I think with one line of code, you can load the graph in, load the graph structure in, though you have to figure out how to set the data yourself. Another thing we can do is say for instance, here's an example. Okay. So this will also show you how you might add command line options. Our command line options is based on Boost program options, which but somewhat simplified, which lets us do shit. There's a bit of power. So finally we could do add attach an option graph. So this will create a command line option called graph, which will be stored inside graph file, the graph file variable, with the initial value graph file, which will be empty. And when you go help, you will call graph input. And then we can actually load the graph structure instead. So let's not do create graph, instead let's do something like this. Graphs out load structure. So this is the graph file, which we passed in earlier, which we will pass as a command line argument. Snap is the graph file type, which is snap from the website snap.edu. We also pass a couple of other graph types like NIPS and so on and so forth, and where we store the graph. Right. And we build this. If you build this, you will see it show up on the command line. I think it ran on a little far further.
Did you check the
used before the stack traces the graph options. So other things we also have is we have a serialization system which can store arbitrary native data types. We can store vector types, integer. We can store vectors, maps, practically every STL container. We can store many boost containers as well, and so you can use that to create very fast load and save functions because the text parsing does take a little while. Right. So one thing which I can show you immediately is PageRank demo 2. Okay, so this is what happens if I implement the options properly. So we can take a graph. So say I think I have the Google web graph here. Okay, so if I just run it now, so this is now parsing the web graph. It takes about a few seconds, 7 seconds or so. Right? So instead what I could do is I could tell it to make a conversion which parses the graph once and then saves it in our native format. After which the native format, which I just saved it for continuous graph.b, will load significantly. This now takes just 1 or 2 seconds to load up. Okay, so as again, this PageRank demo contains a whole bunch of options. So we can try it on say Google. Let's see what we want to try. And CPU is equals to 4. Let's run it. So this is a compute PageRank on the Google Web Graph, and I believe up to a tolerance of 1 minus 5. And should take something like 7.6 seconds. Okay, so while we're at it, let's see the list of options available. Okay, so one interesting thing is the scheduler option. So we have a collection of schedulers. So the kind default one is a sweep scheduler, and what it does is it just gives an array of tasks to execute, and it processes a sweep across it as fast as it can. And we have other schedulers, which FIFO, which is a very classic first in first out queue. We have a queue FIFO, which is somewhat faster. It does this atomic swaps of it fills out queue partially and does atomic swap to put it into a processor. We have a priority scheduler. There's a way to set priorities on your on tasks, and that actually connects back to that question of how do I combine update functors, which I will talk about very quickly. So, and all these can be specified on the command line. So, for instance, let's look at this thing again. Then we can equals to QE. Oh, sorry. And this should run much faster, 5.7 seconds, because the queue FIFO scheduler is quite a bit more efficient. Another interesting option. The video is going to lose some force. So another interesting option, which you will see here again, is this mysterious scope option. So it defaults to something called edge, and there's a few other options like non-vertex edge and full. And just out of curiosity, let's see what happens if I run scope equals a vertex. .7 seconds. Now, what does that scope equal vertex thing do? Okay, so let's bring this back to the top. So this is okay. So what happens happens with scope equal to vertex is that it relaxes consistency. It relaxes the consistency into something much weaker, essentially allowing these races to appear. Right? And if we run the scope equal to vertex, we do observe that if you misimplement your update function such that kind of races actually cause some amount of data corruption, you may never actually convert properly to the correct answer. And this is actually an evaluation of running on, I believe, a reduction, I think it's a domain graph. And as we run it, you can see we run it consistently, it kind of converges nicely. If we run it with scope equal vertex, we get this big fluctuations, and this is error to the ground truth. Okay. Now, so what does this mean? So let's write consistency. So consistency, we have this, the idea is kind of there's this trade-off between consistency and throughput, where throughput is this number of iterations per second, how many iterations can I run per second. But really, again, this is a false trade-off. This is not really what I want. The goal of a machine learning algorithm, the goal of any algorithm is to converge, get the correct answer at the end. Right? And so part of the goal of the Graphlab design is to permit the design of race-free code. So that within the Graphlab, we would like to be able, the user to be able to tell us how much can computation overlap. Right? So for instance, here we have 3 update functions. They are running in parallel, with 3 processors running in parallel. So all these update functions are all running at the same time. I will run an update function here. So technically, because the update function, so in PageRank we only modify current vertex. But the update function can really modify any of the data within the scope. So we could actually get right races on the corners here. And this brings us to the last component, which is the consistency model. So the reason for consistency is just to drive the point again, is that machine learning development cycle has, so traditionally there's a field test loop which all development processes go through. Machine learning has this fourth thing of tweak the model. Improve the model, we go back and we try it again, we make improvements, and it's important for the framework to behave predictably and consistently and avoid problems caused by non-determinism. So is the execution correct? Is our execution wrong? Or is the model wrong? So of course, we do find empirically that there are many algorithms which just behave fine if you let them release, right? But the thing is that when you are developing a model, you may not want to try that. When you develop a model, you may actually want to try to run it consistently, have it work, evaluate, and then evaluate it when running inconsistently. And maybe it work, maybe it won't. So we have 3 modes of consistency. The first is full consistency, in which this is guaranteed same for all update functions, and the way we do it is by guaranteeing that no scopes overlap. So we are giving parallel updates 2 vertices apart, and therefore we have as valid doctrines for parallelism. Now we find that this full consistency has to be way too strong for many applications, and that parallelism we can pull out this for a lot of computation, for most computation tasks. So in practice, what is more common is age consistency, where not all, because most other functions only need to access and read from ages and vertices, possibly modify the age data and modify the vertex data. And so age consistency is sufficient, where we guarantee the update functions only 1 vertex apart will be run in parallel. So for instance, all these 3 things can run in parallel. And finally, in the weakest case, we have vertex consistency, where it is really only safe, truly safe for map operations on vertex data if you only read from edges and edges your current vertex, and you can just unschedule all vertices to run parallel ones. And that explains the collection of options we saw earlier. So there's a vertex edge. So naturally, vertex consistency gives you a lot more performance, a lot more parallelism, but the question one must always answer is that does the algorithm actually converge. You will actually want to come out, look at the answers, and see whether it makes sense. And later on in Carlos's talk, we will have a few more examples where this will fit. So one other thing that we also support is something called shared variable, and essentially it's a global aggregation operation through a kind of synchronization framework we call. And all it is a parallel reduction over all vertices. And so we can use this, for instance, to compute the highest page rank. Or we can use this to compute maybe a lot like as a program is running. So this synchronizing operations computed while the program is executing, and your other functions can read from it, or you can just use it for print out, or you can use it, for instance, one thing very useful, you can use it for parent and learning. Okay, so sync variables are, we compare some predefined intervals while other functions are running. And so that brings us to the source code interjection 2, where I will demonstrate if I can find it. So I will drop the entirety of a synchronization operation here. It is a little long, but what this does is it computes the page with the highest page rank. Okay, so what happens is that when it's a multi-core system, okay, we have 4 processors. Each processor is going to instantiate 1 copy of this accumulator class. Okay. Operator parents will be used to call this operator class on each vertex in the graph. So essentially, we have 4 processors. Each processor will kind of take care of 1/4 of the vertices in the graph. So this context is the same context as you've seen earlier in the other function. So what we do here is that we see if the vertex value is higher than the top rank we've seen so far, we store it, and we also store it in the next page ID. And then after all of these, all the vertices have been touched, we combine the accumulators with the class equal operator, and so this combines all the accumulators into one single accumulator, and otherwise combined with a single accumulator finalizes complement, and in this case we output the top page and the top rank. Right. We also have a shared data table system where the finalize operator can write back into a shared table which all other functions can access. And so to quickly demonstrate it, I will run this. The same program, and we get periodically I will output the current highest page and the current highest page.
She said it runs in the back. This runs in the back.
Yes. This runs in the background while all other functions are running. Now, yes, we do science. Yes. Okay. Now, it looks like I may not be able to get to answering your question, but okay, what happens is that the other functors contain state, can contain arbitrary state, which actually I get to a little bit later. And you can define a plus operator, plus equals operator, which combines its operations. So what happens is that if two update functors are scheduled on one vertex, we use the Pascal operator to combine them into one. Right, so you can define your Pascal operator, and with that we can actually exploit to do very interesting things as well. So the question is now, what can we do with all these primitives? So it turns out we can do many, many things. One example is matrix factorization. So matrix factorization is, for instance, with Netflix. Let's say Netflix matrix. We have users and movies. Right? So Netflix sparse matrix, we can think of it as a bipartite graph between users and movies, with an edge between a user and a movie if the user rented the movie before. And then on each user, we store the feature matrix of the user, the movies and the feature matrix of the movie, and the goal is to try to get them to get the predictions correct, which is how highly the user played the movie. Okay, and just to show some quick performance results, this is from an earlier old run we have on a distributed graph experiment where we run on up to 64 EC2 units, EC2 HPC units, varying the dimensionality of the matrix factorization. And we get really speed up, though I think now we have a few more performance optimizations which will push the speed up quite soon higher. So another interesting thing we can do is this video co-segmentation task, where the goal is to discover coherent segments across a video sequence. Right, so for instance, if I assign a video sequence and I label something as road in the first frame, I would like road in the last frame to be labeled the same. Right, and this is a graphical model inference task. It's an EM-like algorithm. We use propagation for inference, and we use a sync mechanism to build up the cluster centers. And we run this distributed around the 64 nodes, and we get very good speed up on this as well. So generally, we find the cost of going from shared to distributed memory is kind of variable depending on the task. Really, is kind of how much computation you do, and so forth. For this task, it turns out because we can partition the graph very well across machines. The cost of going from shared to distributed is very well. So this will actually go down to 1. The line will go into quite straight. So there's a lot more things we can do: tensor factorization, optimal inference, some units of vector machines, clustering, linear solvers, SVD, etc. And you can talk to Demi, who has built a ton of different applications within Graphlab.
Can I ask questions?
Yes, let's do that. I think I will go on to some of the other Graphlab tools. I don't think I can spend to do more code demos. So, yeah. Does anyone have any questions so far? Yes.
About the consistency of them, when you make it, the vectors you still use them to maintain the consistency.
Yes, exactly. Actually, yes. We currently use a set of rewrite logs to maintain consistency in the shared memory setting. We are looking into ways to make it faster. It's actually kind of tricky. So in the distributed setting, maintaining consistency is a bit more complicated, and we have a series of methods involving very heavily pipeline distributed model to manage that.
And you can use that system to make it faster than shared memory?
Yes, so currently our internal scheduler data structures are not particularly log-free, but we are looking into making them more log-free. So something which I don't want to look into is the use of speculative logging on the graph itself, because if my graph is very large and only 8 processors, the just the probability of any two processes colliding is only very low. Where I have not, this is something we're looking into, we don't have we don't have English.
The graph is sparse to assumption.
Yes, if the graph is sparse, then the graph is less sparse and we're not noticeable. But yes.
In your code example, you loaded the graph into memory, right?
Yes.
Yes. Like, how is this the same code if you have it distributed, or?
Okay. So
there's some examples. If it doesn't fit in memory.
Let me. Oh, so even in the distributed version, we require it to be in distributed memory. We don't have an op-core implementation. This is actually with probably problem pieces, but we don't have an op-core implementation yet. So the graph has to be partitioned and fit in distributed memory. Right? And so in the current Graphlab, actually so I was planning to do something like distributed, but currently Graphlab the gap between shared and distributed implementation is not too large. You should not have to do a huge amount of code to move between shared and distributed. It's not the idea. And just to show this is the gap between the shared and distributed version. There's a diff on the left side of the shared version, on the right side of the distributed version. And there are not too many differences. In particular, the vertex data is the same. We need ways to serialize the data to transmit across the network. Now we have a distributed graph type. The actual contents of the update function is identical. No changes at all. Because again, we need a bit of serialization stuff. The accumulated is exactly the same. No changes to it at all. But again, a little bit of serialization information. There's a bit of standard overhead involved in setting up the distributed system. But otherwise, we are trying to make it, at least in from shared to distributed, as painless as possible. The one difficulty which might arise is actually the construction of the distributed graph. So I get this good parity if I could load my original graph in shared memory in the first place, and then I could write it out to a distributed graph representation. All right, but so we are looking into better ways of building of constructing a distributed graph. Just an interesting idea is we might, because I'm working with is that how it was? Mate is for Spark, where you can use Spark to construct the graph, and then we take over with it in the Graphlab code. So we could actually use Spark, really a reduced system, really to construct the graph, and then we take over for the actual execution. So we're looking into those possibilities as well. So, yeah.
You want to talk about performance, ballpark relative to existing like our multi-core systems. Yeah, it was close.
Yeah, I don't know. Yeah, it's hard when you have two faults on the Graphlab. So they kind of overlap too much in that. But the cost of sharing the distributed is highly variable. It depends a lot on the graph structure, it depends a lot on the communication. In one particularly unusual case involving the leaf propagation, I had a distributed implementation run faster on one machine than a shared implementation. It's probably because the distributed implementation has more, the log implementers are somewhat different. And yeah, that's going faster, and if I scale it, it goes even faster. So it's highly variable. Okay, now I will just quickly wrap up with some of the Graphlab to abstraction changes. Provide an overview for a couple of them, come to the top for the rest. So one thing we can do is that because update functions can store state, we can exploit them for the greater good. In particular, because update functions store state, the scheduler schedules update functions instances, not it doesn't schedule a class, it schedules an instance of update functor. So we could use update functors as a means of control asynchronous message passing to communicate between devices. In particular, we could write PageRank entirely in this way because I'm not going to walk you too much of the code, but essentially the key idea is that as I modify, I know exactly how much I'm going to affect my neighbors. So I just transmit a message, in the form of update functor to all my neighbors to tell them how to update themselves, to tell them how much to change. And then, but this again might take advantage of the fact that if I have multiple update functors scheduled on one vertex, they just combine using the classical operator that lets me do this fully commutative associative combination, which let's say classical combination framework, which turns out to have extremely fast performance for PageRank. Amazingly fast performance for PageRank, and the cool part is they all converge the same answer. PageRank being is guaranteed to converge the same answer, kind of almost everything else pretty much. So obviously not all combinations can be written this way, but when it can, it's extraordinarily fast. So another thing we're introducing is something called factorized updates. So the idea is one parallelism within a single update functor. So we can imagine that if I have an extremely high degree vertex, then no parallelism can be obtained if in the original framework. If I have 100 million degree vertex, right, on the web graph or something like that, the Google or Yahoo is kind of the 100 million other things. So we don't get any parallelism out of that. So so this is actually, I think it's the same PageRank update as we've seen earlier in the code. And the key idea is notice that we cut it into 3 pieces. We have a loop over images. We make a computation to update the current vertex data, and then we have a loop over our images. Right? And so we can think of it this way. Where we gather, which is kind of a map over a reduction over all my edges. We have atomic apply on my central vertex, and then we have a scatter operation, which sort of perform rescheduling. And this is basically, this lets us write this kind of split update functions scheme, where the code is pretty much exactly the same as before, just split into a gather phase, an apply phase, and a scatter phase. I will not go into much details about this, but nevertheless we'll go into more details of how the abstraction behaves later. And we go to this later, where everything PageRank, which helped us factorize and everything in the command line option. And again, first we can do some work. So we are looking at extensions. The key idea is looking at extensions to improve performance on very, very large graphs. So we learned that increasing by an order of magnitude generally requires a redesign. Every order of magnitude we requires a rethought of data structures, rethinking of how we do things. So going from shared memory to distributed was very difficult, and now we are trying to scale distributed implementation. Currently, we do scale up to about 128 machines. EC2 is where we evaluate 128 machines. And we can handle on the order of 8 billion edges. Now, or billion to 10 billion edges. Now, to go up to 1 more or 2 more orders of magnitude, our distributed graph data structure cannot handle it very well. It kind of collapses. We run out of memory, we run a lot of stability issues, and more better redesign. We have a redesign in progress. And things to look at better graph partitioning for distributed setting. Off-core graph storage, as you mentioned, is something very important. Especially your graph could, it not just could be just on some scaffolding like this, could be like a graph database, and you just like to run things from your graph database directly. and continue changing graphs, for instance. And we can only rewrite this graph that which come back May and we can see it. And then that's it. We could look at the everything picture. It has all kinds of options, but one thing we could do is that equals delta 1 minus 5 decimals.
single machine scheduling implementation, and so we can